I want to talk to you about standardization with censorship. Not only am I going to be able to show you standardization with censorship and the assumptions that we're going to need to make in order for this to work, this is also going to be a good segue into another assumption that I didn't really get into last time with standardization. So let's understand what standardization with censorship would entail. So we have some original treatment that we are interested in, say a drug, and then we have some Y outcome, heart palpitations, that we are interested in. Now, we are conditioning upon one common effect that they both have. Heart palpitations may cause death, or like arrhythmia or something like that, heart arrhythmia or something. And then the treatment, the drug itself, also might cause death. So we're conditioning upon them being alive in the end, because if they died, we couldn't necessarily measure the heart arrhythmia or whatever that they had. Okay, so this is the situation that we're in. So let's say, back to sort of our original example, we have two types of populations. We have one population that is, I guess this is the severe population, and we have one population that is the mild population. The severe population, according to our sample, makes up 30% of all patients, and the mild population makes up 70% of all patients. Based on their severity, the doctors will assign them two treatments. So the mild ones will only get a, let's say, 25% chance of treatment, so 25% chance of A. And the severe patients will get a 90% chance of treatment, so a 90% chance of A. Now there's one more thing here. So these patients, after they get treated, and after they have been segmented into their severe and non-severe populations, will survive. So let's say that we have 15% of the population on the severe case will survive. This is C. And 30% of the population on the non-severe case will survive in this case. So I'll go ahead and say this. Survival will be C equals 0. C equals 0. Okay, this is kind of the full information that we have here. Now we can go ahead and compute the causal effect. We can easily compute the causal effect within this population. Now I want to write out the causal effect that we're going to compute, and I'm going to tell you why we can easily compute it. So the causal effect we're going to compute is, again, y sub A minus not A, right? This is just causal effect notation, of the population of severe patients that survive. Double condition. So we go ahead and put these two conditions here. Why can we easily compute this? Well, because we know the treatment is exchangeable within this subpopulation, right? We have defined it to be exchangeable. We randomly allotted people to be treated or not. And we can, of course, easily find it within this subpopulation as well. So y, in this case, L equals 1, C equals 0 of A minus not A. Okay, so we easily did that. Now, here's the problem. We can find the average causal effect of those that will survive, right? We can find the average causal effect of those that will survive. But perhaps we are interested in the average causal effect in total. So I guess in this case, we would really only be interested in the treatment effect on those that did survive, right? Because, you really just, if someone dies and they died while having arrhythmia, it doesn't really matter, they're still dead. But another example could be, we'll be restricting our analysis to workers that are still working in the factory. And maybe we want to know what the causal effect is on workers in general. So workers that may have worked in the factory in the past. Okay? So what can we do in this situation? Well, other than sort of just explaining that, hey, we only really care about C equals 0, we can do one more thing. And this one more thing is we can assume exchangeability within the C populations, within death and no death. So we can assume that if we were to measure the arrhythmia in patients that died, that causal effect would be the exact same as if we were to measure the arrhythmia in patients that had not died. So we can assume exchangeability within subpopulations. If that is true, we no longer need to condition upon C. We can ignore this conditional, because if we condition upon C equals 1, then we would necessarily be getting the same effect as if we conditioned upon C equals 0, and vice versa. Okay, so if we assume exchangeability, then we're back to our original situation, and this is really nice. So we can compute quite easily the average causal effect for the entire population. And this will equal, we'll go ahead and we'll take the 30% and we'll take it down. So we'll take 0.3% of the population, or 0.3 fraction of the population, times the average causal effect of that subsegment of the population, plus 0.7 times the average causal effect of this subpopulation. So once again, we simply take a weighted average of these causal effects. We were able to ignore the conditioning on C, so we were able to ignore what the resultant sample size was, so 30% or 15% of 30%, and we were again able to just look all the way back to our original population that we had studied, 30%. Now, this brings up an interesting point. What matters here in these sort of 0.3 and 0.7 levels is not necessarily the amount of patients that we ended up studying. So for example, the amount of patients that we ended up studying here was far less than 30%. The amount of patients that were treated in this case is far less. It's 30% of the entire population, then 25% of that, and then 15% of that we actually measured and that were treated. But instead, we extrapolate all the way back up to the original population. And this can be important. So let's say, for example, that L0 was actually a dummy variable for, let me just go ahead and write this nicely, for men, and then L1 is a dummy variable for women. If this is true, we might get a sample, because of just the dynamics of the study, in which 30% of our sample was men and 70% was women. However, we would know that in reality, the true population, so in the real world, the true population is something along the lines of 50%, or 49, 51. And I'll just kind of ignore that here. And so if we knew this through some hook and by crook and just by sort of a realization of reality or by talking to experts, we could go ahead and we could substitute these 50% down here, which are better estimates of what the true population would be. And in such a way, we can get a better estimate of the true causal effect, the average causal effect of the entire population. Okay, so I hope this has been super elucidating for you. If you guys have any questions, please go ahead and comment below.